Hey everybody, this one is actually going to be short. I promise, really, I mean it, unless I get distracted. Well, let's see what happens. Okay, so we are looking at solving equations today, and you're like, really? I've been doing this since I was 3 years old. Uh, Man, kids get smarter every year. But the point that I want to make here is that this will be about solving equations, specifically using a couple of numerical methods that I hope you will find useful. So let's do it. When we are looking at linear equations, so this is like the content from last time, we've got x plus y plus z equals yada yada, these sorts of systems. So we've got Gaussian elimination and we have matrix inversion as two of the tools in your toolkit. Those are things that can be done by hand. Inverting matrices by hand, not recommended, but is possible. Gaussian elimination is great. Love it. Highly recommend. 10 out of 10. And you can just go straight into Python or any other programming language and write routines for solving systems of linear equations by Gaussian elimination or by matrix inversion. There are even pre-built solvers out there that will implement these algorithms for you, but they're really not too bad to write up yourself because they're not actually that complicated. Again, matrix inversion is computationally painful in terms of the number of just raw computations that have to be done, but it's not complicated to write down the formula and then do it. There are a couple other methods that I did not mention last time. So LU decomposition, LU stands for lower and upper. This is basically Gaussian elimination on steroids. So you are taking that coefficient matrix and doing row operations to separate it into an upper triangular part and a lower triangular part. And I'm not going to get into the details of it today, but it is a method that is pretty popular as a way to implement Gaussian elimination in a computational context. So if you ever find yourself in need, look it up. It's a good one. Cramer's rule, this is something that occasionally people learn about in like their algebra 2 or pre-calculus classes, and usually in the context of 2 by 2 systems. It does generalize to n by n systems. So I will talk about Cramer's rule for just a minute here. And it's not this Cramer, it's a different Cramer. Uh, so moving on. Cramer's rule, here it is. This is why I love this is it's just a turn the crank formula. You just do the same thing every time. It doesn't require any creativity. Um, and you use determinants of matrices to calculate the solutions to your system of equations to get the values of the variables. So I took this straight from the LibreText Math Pre-Calculus book. It's actually a really solid book. I do recommend it if you ever need to look up some more foundational math stuff. But the way the algorithm works, the way you do Cramer's rule, is you set up your system of equations, you write your coefficient matrix. So that is the just big D here. This is our coefficient matrix. And then what you do is for each variable that you want to find the value of, then you create these substitutional matrices that are like the coefficient matrix, but you replace the column corresponding to the variable you want to know. So like if you want to know x, then you replace the first column, because x is the first variable, with the inhomogeneous terms from the equations. And then you calculate the determinant of that thing, and the value of x, the final solution, is just the determinant of the x substitution matrix over the determinant of the coefficient matrix. And this works with all the other variables. So for y, which is the second variable, you replace the second column of the coefficient matrix. And for z, you replace the third column of the coefficient matrix. And that's it. Like it's very straightforward. It's a really elegant little solution. I'm not going to prove it because it's a lot of annoying algebra, to be honest. But why might you use Cramer's rule instead of just inverting the coefficient matrix? Because, I've said like, hey, doing inversions is a pain, and that's true, but this is doing, like we're doing 4 determinants to find 3 variables. So is this any better? The answer is, of course, it depends, because that's always the answer. One situation where Cramer's rule is clearly superior is if you only need the value of one of the variables. If it's like, I only care about y in this problem, it doesn't actually matter to me what x and z are, then you can just do 2 determinants, divide them, and you know the value of y, and then you're done. And you haven't wasted the effort of finding x and z along the way, or calculating them in parallel by doing the matrix inverse business. So that's a place where Cramer's rule is definitely better. On the other hand, I think I mentioned this last time, but inverting matrices isn't always painful if the matrices are sparse. So sparse is a term meaning that the matrix has uh, many zeros in it. Then in that case, inverting the matrix can actually be quite fast. There are tricks for inverting sparse matrices. And then in that case, you may actually find that doing the inverse is faster than doing a whole bunch of determinants to find all the individual variables. Yeah, so that's Cramer's rule. I'm a big fan. This is one of those things that is just a nice trick to have in your toolkit because it is useful just often enough to be worth the brain power that you have to use to store it. Okay. And Cramer's rule is very straightforward to implement in code because it is just a fixed algorithm. Make an array of numbers, calculate the determinant, divide, you're done. So in that sense, it is pretty nice. Okay, so that was systems of linear equations. But I actually want to talk about more generally nonlinear equations for the rest of this video. And we won't look at systems of nonlinear equations today, but we will look at single nonlinear equations, and then you can go learn the rest from there if you ever need to. Now, when we're looking with experimental techniques at materials, we're doing property measurements, maybe measuring strength with relationship to composition or anything like that. There's always going to be noise in the data, but also, as this bullet point has been hinting, we're pulling individual data points from some underlying relationship between two variables. It's not just random XY points on a scatter plot. The idea is that we have measurements that have some error in them, and there's error, it's always coming up. So we have some measurements that have error in them, but those measurements are drawn from an underlying functional relationship. And so each of the points we obtain is sort of the true function plus or minus some error. And in that case, there are a few different options that you have for how to solve the equation represented by those data. So one method, which I'll show the example of next, is just straight up brute force. You can go through every single data point and be like, is my y coordinate positive or negative? If it's positive, and then the next one is negative, oh, it must have gone through 0 in between. Now, the noisier the data are, the more false positives that method is going to turn up. So I'm not saying it's always ideal, but if your data are not too noisy, then this process of just going through all the data points and seeing when the sign, the SIGN, changes is very simple. It may or may not be slow depending on the size of the data set. But another option that you have is to, since you believe there is a functional relationship connecting your data points, you can fit a function to the data, which you've already done in this class. Crazy how that works. It's like we're building up skills on top of other skills. It's almost by design. Okay, sorry, I just had to have a moment. So you can fit the function to your data and then find the zeros of that function. You're like, how is that different? Well, it's different because we have lots of tools for solving equations once you know what the equation is. But let me show an example of this brute force method first. So just qualitatively here, this is my data set. So it represents some function. Maybe it's even supposed to be linear. I don't know. Uh, and you can just tell by eyeball, like, okay, there's a 0 in this function. There's some f of x equals 0 point somewhere around here. Somewhere around there. Where'd my eraser go? Oh, geez. Okay, great. So our 0 is somewhere around there, but we want to know a little bit more precisely where that is. And presumably you want to code this up so that it's automated so that you're not hunting for zeros by hand. So you check all the signs of your data points. Positive, 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 negative. Oh, okay. So the 0 is somewhere between those 2 points. Those 2 points are the ones of interest. What you do then is you do a linear interpolation. So you are going between the two data points and finding the right location between those points. So you draw a line through the 2 points. This is back to algebra, like point slope form kind of stuff. I have y1 and y2, I have x1 and x2. I can write the equation of the line connecting those 2 points, and then you can solve for when that line equals 0. And you're like, oh, it's 0 right there. There's my point of interest. So that's how this works. If you have zillions of data points, obviously this is going to be very slow because you're going to be going through zillions of data points trying to find probably a few zeros. But if your data set is not huge and the expected number of zeros is not huge, this can actually be pretty fast. But that's our searching method, just by looking for sign changes and then doing interpolation between the relevant points. But I mentioned before that usually when we're dealing with physical data, we believe there's a functional relationship between variables. So in that case, uh, I recommend doing a polynomial fit unless you know the function that the data obey already. Like if you know a relationship is exponential, yeah, do an exponential function. If you know the data are sinusoidal, use a sine function, like a course. But if you're not sure what the relationship is, a polynomial is a safe place to start for 2 reasons. First, finding roots of polynomials is easy. And second, as we've learned from Taylor series, you can approximate almost any function with a polynomial, and the approximation can be pretty accurate if the polynomial has enough terms. Not all functions, but most. Most well-behaved good physical functions can be approximated well by polynomials. So you fit a polynomial to your data set, you know how to do that already, and then you use the roots function in NumPy. You feed it the polynomial that you have fit, and then you say find the roots of the polynomial, and then you're done. It's so easy. This is great. If only we knew how to find roots. But like, how does the computer do it? We don't want magical answer boxes. We want to understand what's happening. One popular option is Newton's method. Now, history of math, Newton did not actually invent this method. It was probably invented in Persia in the Middle Ages, like 1100s, 1200s, I think. I didn't go down too far in the rabbit hole here to really like dig up the history of this method. Maybe I'll do that for fun someday. Um, but the reason Newton gets the credit is not just because like he's a big famous European with lots of clout or whatever. Uh, Newton was really the person who used the modern language of calculus as we understand it today to justify and use this method using modern calculus. And so that is actually kind of a big step, and he deserves some credit. But yeah, Persia. Okay, anyway, how does Newton's method work? What you do is you start with a guess. You're like, I think the 0 of my polynomial is somewhere around here. And then you approximate. You say, okay, I'm going to find the value of the function at my guessed location. But then I actually want to work toward a better approximation for the root, because x naught is almost certainly not the exact root. It's just somewhere close where the value of the function is pretty small. It's a good guess. Hopefully it's a good guess. So then you take the value of the function there and you compare it to the derivative of the function. And you're like, that's kind of weird. Why would I divide a function by its own derivative? Well, what you're doing is you're calculating delta x, because the value of the function is really y, and then the derivative is dy dx. So if we take y over dy dx, that's kind of like a delta x term. I'll show that graphically in just a second. So now we're saying I take my guessed x, and then I adjust it by a delta x calculation, a linear approximation to delta x, just using the first derivative. And so then you get closer to the true root. And now this method works iteratively. So you take your solution, you plug it back in. You get delta x from your new x1, and you remove that to get to x2, which is even closer to the true root. And you repeat that as many times as you need until you are within 0 to some acceptable error level. And you, the person, have to decide how close is close enough. Okay, so I said graphically there's justification for this. So here's a plot. The red alpha curve here is our true function. And we're going to start by guessing at x naught. So at x naught, that function has some value. That's the f of x naught in the first equation. Well, if I take the derivative of that, that's indicated by the blue line here. So I draw a tangent line to the function using its derivative, and then I follow that tangent line backward until it hits the axis. That intersection point, if the function is well behaved, if it's like continuous and differentiable and kind of standard math requirements, if the function is well behaved, this new point that I got from drawing the tangent line backward is going to be closer to the actual 0 of the function. And so now I take that point, I find the value of the function at that point, I draw a new tangent line, follow that tangent line backward until it hits the axis, and that gets me even closer to the 0 point. And you continue this as many times as you want until you're as close to the true value as you want to be. That's Newton's method. That's actually the whole thing. It's not too crazy. Now, how do we implement these things? Python has a variety of libraries for solving equations. You can calculate things yourself. It's good practice. You'll certainly learn something from it. It's unlikely to be faster than what's already out there, if we're being honest, unless you're a programming wizard, in which case, why are you even here? Okay, but one I will point out that's come up a lot in my reading is the optimize library in SciPy has this fsolve function inside optimize. And I found a really nice reference while I was researching for this video. It is hosted by Berkeley, and it's this open textbook called Python Numerical Methods. So that resource is something I definitely recommend. You can check it out if you want to get further into this stuff. It also has just like some basics of programming in Python and other useful background info, which I know with all of your free time, you'll be sure to read it. But it's out there, so now you know. All right, and that's everything I wanted to say, except for my last point, which is that these methods require guesses as input. So how good your guess is determines how fast and how accurate the final solution will be. If your guess is bad, the answer will be bad. If your guess is good, the answer will be good, and you'll get there faster. And this just reinforces that point of, even though you have the computer doing a lot of the grunt work for you, it still really does pay to understand the system, know how the math works, and be able to give good instructions to the computer. It will make your work better in the end. And that's, from a utilitarian point of view, why I do emphasize being able to do math by hand and thinking about functions and graphs and behavior and all that. From a principle point of view, it's also just good for you as a person, and it's good for your brain. And you should invest in yourself, because getting smarter is a good thing. All right. Why this matters in real life, that's what the next video will be, so I won't spoil it here. I'll see you over there. Have a good one.